So today we're going to continue pretty much where we left off with antiderivatives. It's going to be a bunch of different methods of taking the antiderivative of a function today. We'll look at something called integration by substitution in particular. Let's get started. So today's plan will continue to develop our understanding of integration, which again is finding the antiderivative of a given derivative function. We'll talk about sum and difference integrals to start again today. We did those last class as well. And then, like I mentioned, a new method called integration by substitution, which is basically a way of taking an antiderivative to save us a huge amount of time for the more complex ones, especially the ones that seem to involve chain rule. We'll do a ton of examples with this. That'll be the vast majority of today. You'll probably want to follow along with a few of them. Some of them might be a bit tough for you to try, especially early on, but hopefully after you see me do a few of these examples here, hopefully it gets a little bit easier. Anyway, let's get rolling. So first of all, this is a review one. I do want you guys to try this one on your own. So you'll want to pause the video here, give this one a shot, and I'll go over it right now. So this is a sum and difference antiderivative, just like what we did last class. Basically, if you have a bunch of things added or subtracted together inside of an integral, you can just take the integral of each individual piece. So bottom line is, we can break this apart to the integral of 5x cubed dx, that means with respect to x, minus the integral of 2x squared dx, plus the integral of 10x, 10x, there we go, dx. Now it's a good idea to put dx inside of each of these because, of course, with each of these integrals, we are taking it with respect to x, so we should put the dx there. That's just kind of our pointer that guides us where we need to go. Now we'll take the antiderivative of each of these steps. You might remember, hopefully, that when you take the antiderivative, unless you were given some initial condition, you're supposed to say plus c. We'll save it for the very end, though, because otherwise all of these will have a plus c, and we'll just have to combine them. But anyway, here we go. So first one, the antiderivative of 5x cubed. Usually I just focus in on the power here. That's going to make sure we have an x4. That 5 is also going nowhere. If we had 5x4, remember the 4 would drop down. We need to get rid of that because it didn't show up here, so we'll divide it by 4 instead. That way, what we can say is we took the derivative of this, the 4 comes down, knocks out the 4 on the bottom, and we have 5x3, which is what we started with in the first place. Again, these get easier the more you do them. They're always kind of a bit of a brain puzzle for sure, but it is what it is. Anyway, minus 2x squared. Well, that's going to become 2x cubed, but we have to deal with the fact that that 3 is dropping down. So we'll divide by 3 so that when that thing drops down, it just gets canceled out. Plus, same idea here, it'll be 10x squared. But remember, we want to get rid of that 2, so we'll divide by 2 on the bottom. As I mentioned briefly a moment ago, when you take the antiderivative, you're going to have a plus c. I didn't have to put it for each and every single one of these. That'd be a waste of time. So now that we finished it, we'll just say plus c at the very end. Now, what I like to do, I guess like this is pretty much good enough, but what I like to do is I see if I can clean up any of these fractions here. 5x4 over 4, there's nothing we can do there. Same with 2x cubed over 3, nothing we can do there. But 10x squared over 2, that can simplify down. So as much as this is kind of a silly, simple little step, it still is really important to do. So we'll say this is 5x4 over 4 minus 2x3 over 3. And then this is just plus 5x squared. And then, of course, our plus c. There we go. Okay, anyway, moving on. Let's move on. All right, I don't want you guys trying this one on your own because this is a tough one, but I do want to walk you through this and hopefully get your brain kind of turning as we're going through it. So just like the last one, this is a sum and difference integral, so we can just break this apart into its pieces. This is going to be the integral of e to the power of x dx plus the integral of x to the power of 2/3 dx minus the integral of 1 over x dx. Now, the middle one is probably, actually, believe it or not, going to be one of the easier ones here. These other ones on the sides, they're kind of weird. We haven't seen anything like this in a little while. You might remember e to the power of x. That's a very special function because in calculus, if you took the derivative of e to the power of x, it still is e to the power of x. It's actually the only function that does that. So the integral, likewise, is going to be the exact same thing, right? So the integral of e to the power of x is also e to the power of x. So that actually was pretty nice. The hardest part was just remembering that that was a rule in the first place. Plus, this middle one, it's just a power rule thing. So we know this exponent's going to have to go up by 1. That means it's going to be x to the power of not 3 over 3, but 5 over 3, because that is 1 whole bigger than 2 over 3. And then, of course, we got to get rid of that 5 over 3. So I'll divide by 5 over 3 on the bottom. We'll deal with that fraction on there a little later, but we'll just leave it there for now. Now, this one on the far right, this is probably the most challenging of the bunch. This is 1 over x, of course. You might look at this and say, oh, well, that's just x to the negative 1. So that just means I got to like drive the power up by 1. So it'll be x to the power of 0 and then over 0. But obviously you can't have that. That's why I didn't even write it down, right? Because x to the power of 0 divided by 0, that's not going to work. Divide by 0, what the heck, right? No, it doesn't work. This one is another throwback, kind of like this first one here. You might remember, and if you don't, it is on your formula sheet, although it's like in a weird implicit differentiation version. You might remember that the derivative of ln x, like if you were to take that and you're taking the derivative of ln x, is 1 over x. So in other words, if we were to go backwards, the antiderivative or the integral of 1 over x is therefore ln x. And then of course we can't forget we also have to have a plus c right there. Other than that, this is pretty much good to go. I just don't like the fact that we have a fraction in this middle term here. So we're going to clean this up. Remember, we have a number divided by a fraction. That's a keep, change this to a times, and then flip. So it's 3 over 5 instead. Long story short, I'll let you do the math. It'll be e to the power of x plus, this will be 3x 5/3 over 5 minus ln x plus c. And if you really wanted to go crazy, you could turn this x to the power of 5/3 into the cube root of x to the power of 5. But because the question itself gave us a fraction as an exponent, I'm not going to worry about that. No point in doing that if they already gave that to us in the first place. So anyway, it is what it is. Let's move on. So we're going to introduce a new concept today called integration by substitution. I want to start with a really, I shouldn't say really easy, but an easier level question here. I want us to suppose we had the integral of 2x cubed dx. So notice 2x is being cubed. Now at first glance, this doesn't look too bad, but what I want you to notice is that the base of the power isn't just x, it's 2x. So it's 2x to the power of 3. Now, that kind of throws a bit of a wrench in our plans here, because if this was just x to the power of 3, we'd be laughing. We'd say, oh, it's going to be x to the power of 4 divided by 4 or something, right? No big deal. But the fact that there's a 2x inside of here, that kind of changes things, because this becomes almost like a chain rule question. Well, an easy way around this in this example is just to expand the 2x cubed first. That's not a big deal here, right? Expanding it out, just 2x cubed, we can do that pretty quick. Now, this isn't really the strategy I'm getting at to here, but I just want to show you this just so it's an easier question to start with so you can see how the strategy works. Anyway, we're going to take the cube of 2x. That's going to be the integral of 2x times 2x times 2x is 8x cubed dx. And now that we have it like this, it's actually not too bad because we have the x cubed just on its own here. This 8 that's on the outside is just chilling. It's not going to really do anything here. So when we do the integral, long story short, this is going to be 8x4, because we had to bump that up by 1, divided by 4, and then plus c. Well, 8x4 divided by 4, of course, that can simplify down because 8 divided by 4 is just 2. So that's just going to be 2x4 plus c. So no big deal. Kind of crazy that that's just how that all worked there. That's actually more than anything, that's just a coincidence. But it is what it is. So really, that wasn't too crazy of a question. But can we integrate this without expanding? You know, in other words, can we actually do this without actually doing that repeated multiplication bit? Now, expanding would be a nightmare if this question had a large polynomial as a base instead. So if instead of 2x, if instead of 2x in here, we had like some big polynomial with like 4 or 5 terms in it, this would take forever. It would be a nightmare. The same could be said as if this exponent was a really big number, like if it was something to the power of 10 or something. You know, it gets tricky pretty quick. So integrating things that typically would involve the chain rule are often more easily done using something called integration by substitution. This is where we substitute, hence the name, the part of the integral causing us grief by replacing it with a single variable. And usually that single variable, we call it a u for whatever reason. This is not actually too terribly bad of a strategy, but it's got quite a learning curve to it. You're going to see early on with this, it's kind of hard to identify what you substitute and what you don't, because again, like this little description here even said, this is usually for figuring out the integrals of questions that seem to involve the chain rule. It's kind of a similar thing where you look at the inner part of the function, but we'll get there. So here's how it works. We're going to use that same example from before, the whole 2x to the power of 3 example. Instead of using a base of 2x, let's make the base u. So that's what we're going to substitute here. Note then the following relations. Bear with me on this one. This is where you might want to pause and rewind a couple times. If we said that 2x was u, so we're changing our problem base to just a single variable. Then we could say that du over dx, this means the derivative of u with respect to x, would be 2. Because imagine if this was the derivative, like imagine u was y, right? The derivative of y with respect to x, you just focus on doing the derivative here, right? So the derivative of u with respect to x is 2. Now, this Leibniz notation, which we've really not been using a huge amount, we've used it every now and then, just rarely. Leibniz notation's time to shine is now. With integration by substitution, you can use this Leibniz notation and take advantage of the fact that it is actually represented as this weird kind of fraction. You can actually take this fraction and break it apart into its du and its dx, which are known as differentials. They're basically acting as pointers in these cases. Bottom line, the easiest way of thinking about it is, like, you don't want to think about it too hard. Just think about du over dx as a fraction. Let's multiply by dx on both sides. So we now have du equals 2 times dx. And then let's get dx all by itself, because if you remember from that previous question, it was the integral of 2x cubed dx. So if we could figure out how to substitute out dx, we'd be golden. Dx would therefore be, if you divide by 2 on both sides, du divided by 2. Given the original equation, oh, here it was right here, substitute what you found and then solve. So here's what I mean by this. We're going to start by substituting the 2x as u. So we're going to have the integral of u cubed, because it's not 2x cubed anymore, it's u cubed. And then instead of dx, which was our pointer to x, we want to make this in terms of u. So let's write in, instead of dx, we'll write du over 2. So du over 2. Now that divided by 2, that can just be put over on this u3 right here, right? So this is just the integral of u cubed over 2 times du. So that just passed it over, no big deal, right? Now this looks like a more typical kind of integral, right? So notice this divide by 2, it's no different than if it was like multiplying by 2 over here, really. It's just a coefficient, basically. So nothing's going to happen to it when we take the integral here. So when we take the integral, we know our exponent's going to go up by 1, so it's going to be u to the power of 4, divided by, we still had 2 down there, but notice that to get rid of this 4, we would have to have also a 4 down there. So really, it's u to the power of 4 over 2 times 4. And then, of course, plus c. Now, here's the thing, of course, u to the power of 4 over 2 times 4. Might as well write that as u to the power of 4 over 8 plus c. And remember, this question was never in terms of u in the first place. That's just what we substituted. So let's substitute this back now. Instead of having u, let's substitute that back in as 2x. So it's 2x in brackets to the power of 4 divided by 8 plus c. And if this was a bigger polynomial here, we'd be done. There'd be no point in expanding this out. But because this is just a single term, 2x to the power of 4, that's pretty easy to solve. That's just going to be 16, in other words, 2 to the power of 4, x to the power of 4. Right? And then that's all over 8 plus c. And then what do you know? 16 divided by 8, well, that's just 2. So it's 2x4 plus c. And bam, look at that. We got it. That's exactly the same as what we had a couple slides ago, right here. Holy smokes, gave us the same answer. So if you're sitting in your chair right now and you're looking at this going, okay, cool, Mr. Scott, that was awesome, right? We did it one way, and then we did it another way. But why the heck did we do it the other way? Because the other way took like 5 minutes, and the first way took like 20 seconds. Why on earth would we do it this way? Well, believe me, you're going to thank me as we go forward with this, because while this example was kind of silly to use integration by substitution, just because of how easy it would have been to expand that 2x, it does have its uses for those questions that have bigger polynomials inside of them, right? So there are cases where doing this method, where you just expand it, is ideal, but there are other cases where, of course, you'll want to actually use integration by substitution, because expanding it would be a nightmare. We'll look at some nightmare cases here, because I think it's really important for us to see both the good and the bad. So here we go. Here's an example of a nightmare case. I don't want you trying this one on your own. I'm going to try this one. I'll go through it with you just so you can see how this works. We've got the integral of 10x plus 7 in brackets, all to the power of 8 dx. If this wasn't an integral, if this was just asking you to take the derivative, you would already know that you'd be doing the chain rule, because you'd have to drop the 8 down and then you have to multiply by this, and it'd be, it'd be whatever. It wouldn't be the end of the world, but it'd be some work for sure. Going backwards, we still kind of have to take account for the chain rule. But unfortunately, we can't really have an easy mechanism of doing the chain rule backwards. So that's where integration by substitution comes in. Long story short, instead of me rambling, how about we just say we look at what the inner part of this function is. In other words, it's the 10x plus 7, and we set that equal to a u. So we'll say u equals 10x plus 7. Before I substitute u in here, we need to figure out something for our dx. So to figure out something for our dx, we have to use the Leibniz notation for the derivative of u. So the derivative of u is du dx. Du dx, that means the derivative of u with respect to x. Well, the derivative with respect to x here is just going to be 10, right? Because 10x, that would just be 10, and then 7 just disappears. We want to get dx all by itself so that we can substitute this back in for the differential as well. So if we multiply by 10x, you're going to see we have du equals 10 times dx. And then if we divide by 10, you're going to see we have du divided by 10 equals dx. That's what we can substitute in for our dx right there, because then at least we're doing our differential with respect to u instead. Long story short, if we go back to the drawing board on this one now with all the stuff we've decided to substitute, this is going to be the integral of u to the power of 8, right? Because u is just the 10x plus 7. And then instead of dx, we're actually multiplying by du divided by 10. Just like that previous example, this divide by 10 can just tack on to the u to the power of 8. So this is going to be u to the power of 8 divided by 10 times du. You might want to skip that step. I just like doing it because I find it easier to read this way. Now we can take the integral, no problem. So if we take the integral, we know it's going to be u to the power of 9. 10 is still going to linger down there. But remember, the 9, when it drops down, it needs to be canceled out. So we need to have a multiply by 9 on the bottom there. And then, of course, we also need a plus c because we just did the integral. Long story short, this is going to be u to the power of 9 over 10 times 9 is 90. And then we have our plus c. But we never want to leave our answer in terms of u. We want to go back to what we started with. What we started with, of course, was u is 10x plus 7. So this is actually in brackets, 10x plus 7 to the power of 9 over 90 plus c. And here's the good news. This is a polynomial to the power of 9. That would be an absolute nightmare to try to expand that. So this is where we get to box our answer and say, you know what? We're done. We're good. That is the integral, the antiderivative, in other words, of our function. And if you don't believe me, the nice thing about questions like this is they're usually relatively easy to check. To check this, of course, you just have to take the derivative of this. Well, the good news is the derivative of plus c is just 0. The derivative of this, though, you'd have to use chain rule on. So the 9 would drop down, which is going to cut this 90 down to a 10, and you'd have an exponent of an 8. And then you have to multiply by the derivative of the inside. So you have to multiply by 10, which gets rid of the 10 on the bottom, and all you're left with is 10x plus 7 to the power of 8, which is what we had in the first place. Awesome, right? So these are often pretty satisfying to check, but unfortunately, they're also pretty easy to make some mistakes on because they do get a lot more challenging than this. Anyway, let's move on. Okay, this one. I don't even know if I want you guys to try these on your own today, to be totally honest, but if you're feeling really bold, you can give this one a try, but up to you. Anyway, I am going to go over this one way or another. If you didn't give it a try, that is fine, believe me. So what I would say on this one is we want to identify the quote unquote innermost function. Now, in this case, this is a Gong show. We've got a square root multiplied by 20x here. If I were to strip away all the nonsense in this, I would say that the most innermost function we can get at is just this 5x squared plus 8. I'm not even talking about the square root. I'm talking about the stuff inside the square root, because the square root really is not much different than a power. It's just a fraction power. That's all it is, right? So I'm going to focus inside this root sign. If you're wondering how I knew that so quick, it honestly just comes out of a lot of experience. Oftentimes, these are trial and error. You could start with something, and if you find yourself going, woo, this is a mess, go back to the beginning and try it again. Anyway, let's give this a shot. We're going to say that u is equal to 5x squared plus 8. Remember, we should always take the derivative of this so we can get something in reference to the dx that we got here. So du over dx, which means the derivative of u with respect to x, is just the derivative of 5x squared plus 8, which is 10x. Then we want to get dx all by itself, so let's multiply it over. So we have du equals 10x times dx. And then, of course, divide by 10x on both sides. So this is going to give us du divided by 10x equals dx. So dx is what we substitute into here. We'll substitute our u that we came up with here into this right here, and we're good to go. So this is the integral of the square root of u square root of u multiplied by 20x. You might be saying, hey, wait, now we got u and an x. What the heck, right? Don't panic. Watch what happens in this next step. This is what's a miracle. Multiplied by dx. Well, dx is du over 10x. Well, look at this. 20x times du over 10x. Well, those x's are gone now. Just totally what I was going to say cross them out, but I crossed it out and I just turned them into a bigger x. That's what I did. Bottom line is those are gone. Mwahaha. And then 20, 10, that's also gone. That just drops it down to a 2. So long story short, what this gives us is we have the integral of 2 times the square root of u. I'm going to change the square root of u into a fraction exponent because that's way easier to deal with. So 2 times u to the power 1/2. It's the same thing as the square root of u times du. And now we are able to take the integral of this just like the old ones we were doing. So here's what's going to happen. If we take the integral of this, the 2 is just going to stay put. It's just a coefficient, no big deal. This is going to become u to the power of 3 over 2 because it had to go up by 1. But we have to take into account the fact that the 3 over 2 is going to drop down. So I'm going to divide by 3 over 2 down here. And then I'm also going to say plus c because, of course, when you take an integral, you always need that. Now, we do want to clean this up, of course. Dividing by a fraction, that's kind of gross. So we keep the top, we change this to a times, and we flip the bottom. Long story short, you're going to have 4u 3 over 2 divided by 3 plus c, of course. And then we need to also substitute back so that we get u all by itself, or u isn't in here anymore. We substitute back in with what we had. So this is going to be 4 times 5x squared plus 8 to the power of 3 over 2. There we go, over 3 plus c. And I guess the final thing that we'll do here, because a fraction exponent's kind of gross and it didn't give us a fraction exponent to begin with, so we should always substitute it back out. Long story short, this is going to be 4 times, well, 3 over 2 as being your fraction exponent. It's going to be the square root of 5x squared plus 8 within brackets inside there to the power of 3. And then, of course, divided by 3 plus c. That is a disgusting answer. Like, that is a miserable, miserable, miserable answer. If you wanted to check this, I would advise you check it starting from this down here, because then it's just a matter of doing chain rules. So if you were to take the derivative of this, the 3 over 2 drops down. That's going to knock some of this out. You're going to end up having basically something over here. And then you have to multiply. Yeah, it's a whole thing. You can try it if you wish. You can take my word for it, though. This is going to work. You will get what you started with in the end. But again, if you want to test it, go for it. All right, here's another example. This one is, it's the first time we've seen a trig example with this integration by substitution. But believe me, it should work about the same. If you want to pause and try this one, feel free. But aside from that, I'm going to go over it now. So remember, focus on the inside of your function. That's what we should always do our substitution on. So I'm going to say u is simply going to be 10x this time, just this piece right here. Now we take the derivative of this so we can get our differential all isolated. So we have du over dx equals the derivative of 10x, which is just 10. And I think you can see if we multiply by dx and then divide by 10, I'm just going to skip that middle step that we always kept doing. I'm just going to say it's du over 10 equals dx. Now, let's do our substitution. This is going to be the integral of sine u. And then instead of dx, we're going to replace that with du over 10. And then that step I always like writing where I go sine u, and then I just bring this 10 into this. So it's divided by 10 here times by du. The divide by 10 is no different than a coefficient, so it's not going to affect this. We have to think about what the integral of sine is. Well, the integral of sine, think about what the derivative would make sine. Well, negative cosine's derivative would give you sine. So we can say that this is going to equal negative cosine u divided by 10 plus c. Now, we're not quite done yet, of course, because we need to substitute our u back out. So this is going to go real quick, though. This is going to be negative cosine, and instead of u, it's 10x divided by 10 plus c. And this one's actually not too bad to see that if you took the derivative, it wouldn't be a big surprise because the derivative of negative cosine is sine. So you'd have sine 10x and then multiply by the derivative of 10x, which is 10, which gets rid of the divide by 10. So yeah, that one wasn't too bad at all. That would be our derivative there. All right, a couple more. And this one looks like an absolute beefcake. Like this is an absolute train wreck looking one here. But remember my strategy. Focus on the innermost part of this function. You will thank me for that later. If you want to try this one, if you're feeling really bold, go for it. but again, I'm going to go over this one. The innermost piece of this whole function, in my opinion, is going to be this 4x squared right up there. So I'm going to start with this. Again, if it doesn't work, you can always dial it back and try something different. But I'm going to start there. U equals 4x squared. Remember, we need our differentials. So this is du over dx equals the derivative of this, which is just 8x. We want to get dx all by itself, so let's multiply by dx, and then, of course, divide by 8x. This is going to give me du divided by 8x equals dx. We now have our differential that we can change out here, so we should be good to go. This is now the integral. Instead of e to the power of 4x squared, it's just going to be e to the power of u multiplied by 2x. Maybe I'll put that in its own brackets there too, just for good measure. E to the power u times 2x. Don't freak out about this, because watch out here. Dx is multiplied by du over 8x. And then what do you know? The x's here, when 2x multiplies here, it's going to cancel out the x's there. And 2 divided by 8 is like 1/4. So this is going to become the integral of e to the power of u over 4 times du. And again, that's because that 2 and that 8 would simplify down. 2 over 8 is 1 over 4. So the 1 over 4 goes on to e to the power of u. Once again, when you have a coefficient on something like this, whether it was taking the derivative or in this case taking the integral, that coefficient isn't going anywhere. And also, when you were taking the integral or the derivative of e to the power of x with respect to x, or in this case e to the power of u with respect to u, it's not going to change at all. It's a very special function in calculus that does not change in any way, shape, or form, which is very, very fortunate. So that tells us that the integral of this is simply e to the power of u over 4 plus c. But wait, there's more. We have to, of course, substitute that u back out. So that's going to go quick, though. That's just going to be e to the power of 4x squared divided by 4 plus c. And that is as far as we can go with that one. And again, if you were to take the derivative of this, the derivative of e to the power of 4x squared divided by 4 is just e to the power of 4x squared divided by 4 multiplied by the derivative of the top up here. So multiplied by 8x. That's where you end up canceling the 8 with a 4 on the bottom. And that turns it down to 2x, and you're done. Awesome. All right, I think we only have one more question on this one. Here we go. Yes, this is our last example. The integral of sine cubed x times cos x with respect to x. I'm not going to lie to you. When I took a glance through my slides here at the start of this, I was like, oh boy, this last one's a little tricky. But there is something to notice here. If you want to try this one, go for it. But I am going to go over this one. So the notation on this one is what's causing, or at least is what caused me some trouble. Remember, sine cubed x means sine x times sine x times sine x. Another way of writing this, if this is confusing, is you can put the cubed on the outside here. This is sine x cubed. It means the exact same thing, one way or another. I'll just leave it how it's written, though. The reason that that's important, since it's sine x cubed, is we can say that u is simply sine x. I'm not going to lie. My first instinct was to say that u was sine cubed x, but if you try that, believe me, you're not going to get anywhere at all. You're going to get like this horrible, horrible expression for your differential, and that's not going to be good. So speaking of our differential, let's get those differentials going. We got du over dx. So the derivative of sine x is just cosine x. And then we want to get dx by itself, so we multiply it over and then divide cosine x over. And watch this. It's going to be du over cosine x equals dx. That looks pretty gross, but believe me, if you substituted the sine cubed x, it would have been a lot worse, like a lot worse. So be thankful on that one. Anyway, we have our substitution. Let's substitute all this stuff in here now. Let's see where we can go with this. So this is the integral. Instead of sine cubed x, since u is going to be our sine x, we might as well just call this u cubed, because u is sine x, so u cubed is sine x cubed, or in other words, sine cubed x. It means the exact same thing. Multiplied by cosine x, multiplied by dx, which is du over cosine x. Look at that. Brilliant. Cosine x, boom. Couldn't have worked out better if we wanted. So all you have left now, this is amazing, is u3 times du. Holy smokes, that is like the easiest one we've dealt with since the beginning of today. So in other words, the integral of u to the power of 3 du, well, we know it's going to be u to the power of 4, because it's got to go up by 1 when you take the integral. But of course, we don't want that 4 there, so we got to go divide by 4, because when that drops down, we want it to cancel out. And of course, we need to have plus c. So that's all well and good. But then, of course, substitute our thing back in for u. So this is going to be sine x to the power of 4 divided by 4 plus c. That works as an answer. You even box that. If you don't like this notation, which whatever, you can just write that as sine 4x over 4 plus c. Both of those are correct. They're both the exact same thing. Wow, so as scary as that one looked, that was like one of the quicker ones we've done so far. Anyway, long story short, whenever you're tackling something that looks like an absolute disaster, something that's going to have some chain rule stuff in it, it's a really good idea to try using integration by substitution. Identify what the innermost piece of your function is, set that to your u, get your differentials going, and go from there. Whew. Okay, so for practice, lesson number 1, antiderivatives. That's in the note package that I gave you guys. Remember, a digital copy is located online. If you have any questions from this, please let me know.